homework sheet. Okay, right. So first of all, let's go for the theory one. Let's start the theory. Okay, and then we'll do the homework and the multiple choice question. Okay, right. So let's start the lesson today. So first of all, I'm going to tell you the importance of the unit 3. Okay, right. So in unit 3, in our final examination, there are like structure also there, essay also there. So like mechanics, we know that when you are taking the final examination, we'll get like in MCQ, we'll get like 6 to 7 to 8 questions in unit 3. Okay, right. And also there will be one structure and another one in essay question. So it's like structure. For this structure question, we'll get like 5 out of 100. For essay question, we'll get 7.5 out of 100. And for this one, let's say we are getting like 8 questions. Okay, so this is like 12.5 and this is 8. So like 20 marks we can get from this unit only, the unit 3rd unit. Okay, right. So this is a very important unit, and let's start the session. Okay, right. In this unit 3, there are 2 parts. We can divide them into 2 parts. Okay, right. One is waves and oscillation. So the unit is waves and oscillation. We can say one part is like sound. Another one is light. Sound and light. Basically, there are 2 chapters. One is sound and another one is light. In sound, there are several chapters. Are there like we can say like 3.1 to 3.67. Yeah, it's sound. And 3.6 it's sound. 3.7 to 3.8 or 3.9, it's light part. Okay, both are very important parts here. So now what we are going to start here is the sound part. Okay, right. Okay, so let's start the session now. The first chapter, 3.1, is simple harmonic motion. 3.1. Simple harmonic motion. This is chapter 1. Okay, right. So this is chapter 1. Can you say like what do you mean by simple harmonic motion? Do you have any idea about simple harmonic motion? No idea, right? So let's say we can divide motions into 3 types. Basically, we can divide the motions into 3 types. One is you can look at the tube here. You can look at the tube. Okay, right. So one is periodic motion. Periodic motion. Okay, right. Periodic motion is, there is the definition they already given. A motion which repeated itself at equal intervals of time is a periodic motion. So can you tell me a motion which repeats itself at equal intervals of time? So can you give me some examples for this one? So one is like motion of all planets around the sun. So normally we know that if there is, the sun is here, okay, the sun is here. So all the planets, it is like rotating continuously, it's rotating, right? Okay. So can you tell me how much it will take to Earth to rotate to complete a full rotation of sun? To complete a full rotation For Earth, it's like 365 days. Yeah, 1 year, right? So yeah, it will take 1 year. It will take 1 year. So can you tell me when you are taking a clock? This is the clock. So let's say this is the hour hand. Okay. So this hour hand is rotating here. Can you tell me for one full rotation, how many hours it will take? 12 hours for the hour hand, right? For the second hand, how many it will take? It will take like 60 seconds, okay? Right. For the minute hand, 60 minutes. Likewise, it is the process, the rotation here is going again and again and again. It's rotating like again and again and again here. Okay, right. So this type of motions also the periodic motion. Periodic motion means a motion is happening again and again and again with the same amount of time. Okay, right. So again, I'm repeating the definition. A motion which repeats itself at equal intervals of time is a periodic motion. Okay, right. Motion of all planets around the sun. You can write down the next example, the second one. You can write down the second one. Motion of the minute hand of a clock. You can, for instead of minute hand, you can put like second hand, okay, hour hand, that's also fine. So motion of a minute hand of a clock. Okay, right. The second one. Can you give me another example for this periodic motion? What about the pendulum, simple pendulum? Do you know the simple pendulum? Right. So this is like a simple pendulum. Here, this is the bob. This is bob, and this is a rod here. Not the rod, it's a string here. When we are giving a small force here, what will happen is this bob will move like this. The bob will move like this. It's going here again and again and again, it's moving like this. So with the same amount of period of time, it's moving. Like let's say for going from here to here, it's like taking 1 second. Coming back, it's taking 1 second. When it's coming here, 1 second, and going the initial place, so it's taking 1 second. So it will take like 4 seconds to complete an oscillation, and it's happening again and again and again and again. So it's a periodic motion. Okay, write down the second one. The third one, motion of a simple pendulum. Motion of a simple pendulum. Motion of a simple pendulum. The third one. Okay, right. The fourth one. Can you give me some other examples? The motion, it will making motions within the time period again and again and again. So it's like, what about the sunrise and sunset? It will happen like within 24 hours now. So write down sunrise, sunset. Sunrise and sunset. Okay, right. Sunrise and sunset. Okay, right. So later we'll do some more examples on that one. So now what I'm going to do here is I'm going to the second one. It's like oscillatory motion. So first one is periodic motion. The second one is oscillatory motion. What is that? Oscillatory motion. To and fro motion of a body around the mean position is an oscillatory motion. What is to and fro? Back and forth, right? It's going like back and forth. To and fro means back and forth. Going like this. Going this side and coming back to this side like this, back and forth. The motion is something like this. Okay, the motion is something like this. Okay, right. So to and fro motion of a body around A mean position is an oscillatory motion. So there is a mean position. This is the mean position. This is the mean position. Okay, so this is what we call mean position or fixed point. You can call this point as fixed point. Write this down. So okay, you can sketch this diagram in the right side of the paper here. You can sketch it here. Okay, right. You can sketch it here. So this is fixed point. Fixed point. Mean position for the fixed point is here. Okay, right. So look at this one. So like examples for this oscillatory motion is oscillation of a pedal or a swing. Okay, right. Do you know the swing, right? So how the swing will move? It will move like this, no? When we are taking a swing, it will move like this. This will move like this. Okay. So this is the motion of a swing. So it's like it has a fixed point. It has a fixed point here. Okay, right. So there is a fixed point and the particle or the swing is moving like going 4 and 2. That means that the motion is like this, going left and right, left and right. So the fixed point is here. From this fixed point, it's moving here and there. Okay, so this kind of motion is known as what? Oscillatory motion. Oscillatory motion, right? Okay, can you tell me, is circular motion is an oscillatory motion or not? This is an oscillatory motion or not? No, this is not an oscillatory motion. Why? There's no fixed point. No, it is like a small, just a circular motion, just a rotation here. So this is not a circular motion. This is not a oscillatory motion. This is only the periodic motion. Then what about the pendulum? It is, yeah, it is, yeah. Pendulum is moving like back and forth. So this is an oscillatory motion. You got it? Yeah. Sorry, sea waves. Right. So for the sea waves, it's like a random motion because we can't give a certain definition for that sea wave because it's a random motion. But you can take this motion. I'll give a good example for that one. Let's say let's take there is a water here. This is the water level. So this is the water, and I'm keeping a ball here. I'm keeping a ball here, and I'm giving a little push to this ball. So what will happen? It will goes down and come back, right? The motion is something like this. So what kind of motion is this? Periodic motion or oscillatory motion? Periodic motion is correct because it's like it's moving like this, no? This is moving like something like this. Okay, right. So going up, coming down, going up, coming down. So it's something like this. The motion is something like this. Okay, this is correct. This is correct. You know that this is correct, right? So I am telling that. So this kind of motion is also an oscillatory motion. Why? Because there is a fixed point. Yeah, at the middle. Don't think that the motion only the left and the right. It can be happen something like this also. Here's the fixed point. This is also an oscillatory motion. Something like this. This is also an what? Oscillatory motion. So it should has what? It should have one fixed point and it want to move like this. You got it? So this kind of motion. Okay. So you got the tudes? Yeah, we are discussing the theory part. So take out the theory tude, and we are now in the periodic motion and the oscillatory motion. Okay, right. So this kind of motions are oscillatory motion. Got it? Yeah. So I'm going to repeat it. I think for you guys, I'm repeating the theory here. It's like we are now discussing the simple harmonic motion. So this is the first topic in the third unit. Okay. right? So in this unit, we are discussing about the motion. Okay, so we want to study simple harmonic motion. Before studying this simple harmonic motion, what we are doing here is we discuss about the periodic motion. So the periodic motion here is, look at the definition: a motion which repeats itself at equal intervals of time in a periodic motion. Okay, is a periodic motion. So equal interval in time. If there is any motion repeats in equal interval of time. Okay, right. Can you give me an example for periodic motion? What kind of motions are periodic motion? That is in the same time interval, it's repeating. The same time interval, it's repeating, like the planet's movement. It's like this is the sun and the planets are rotating. So let's say if this is an Earth, the Earth take 24, like 365 days to rotate, to complete a full rotation around this sun. Okay, so this is also a periodic motion because it's again and again and again it's happening, no? Right. So sometimes it can be very, like, what about the electrons? Movement of the electrons. So how it will move? It will move the, what is in the middle? What is in the middle? Protons and neutrons. So that is in the center and it's rotating. The electrons are rotating. So the rotation of the time period it will take to complete a one full rotation of the electron is a different time period, right? It's different. For this planet, it's different. So what about this clock? When you are taking the clock, when you are considering the second hand or minute hand or hour hand, so if it want to complete a full rotation, how much time it will get? For second hand, it's 60 seconds. For minute hand, 60 minutes. Yeah. For the hour hand, it's 12 hours. So again and again, it's happening within the same time period. So that kind of motions are what? Very good. Periodic motion. Okay, right. Let's move on to the next motion, that is oscillatory motion. Oscillatory motion, the second one. Look at the second definition. To and fro motion of a body around the mean position is an oscillatory motion. So to and fro means what? It's like back and forth. Going, I'm here, this is the fixed point. I'm going somewhere here and coming back to the fixed point. And I'm going here and again coming back to the fixed point. So these kind of motions are what? Like roaming. These kind of motions are oscillatory motions. And also don't forget, this should be also happens between that given time period. That means it want to repeat within the same time period. Okay, not like this. I'm slowly moving here, like once, like I took 3 seconds to come here, like 1 second to the fixed point, and I'm taking 5 seconds to come back to this point, and like the time is changing here. So these motions are not the oscillatory motion. It should be in the equal time intervals. So that kind of motions are oscillatory motion. Look at the oscillatory motion. To and fro motion of a body around mean position is an oscillatory motion. For example, oscillation of a pedal or a swing. When you are considering a swing, look at this motion. Look at this motion of a swing, how it will be. Like it's going here, coming back to this fixed point, and coming again here, and coming to fixed point. Likewise, it is moving something like this. Okay, so the swing motion is also a oscillatory motion. Okay, right. What about the simple pendulum? When you are taking a simple pendulum, this is a string and this is the bob. So it will, when you are taking, when you are giving a small force here, what will happen? It will move something like this. So that's a fixed point. So the fixed point is here. From this fixed point, it want to move back and forth like this. These kind of motions are what? Oscillatory motion. Okay, right. Right. Okay. So now you know that some examples of periodic motion, the oscillatory motion. I'm going to ask you another question here, guys. Okay, right. Can you tell me? Yeah. Can you tell me? I'm giving a statement for you. The first statement here is all oscillatory motions are periodic motion. Is this correct or not? All oscillatory motions are periodic motion. Yes. Why? Because all the oscillatory motion means that that should have a small fixed point, that should have a fixed point, that's okay. And it should happen within the same time period. So if a motion is happening in a same time period, that is periodic motion already. So all oscillatory motions are periodic motion, but all periodic motions are oscillatory motion. Is this correct or not? It's not correct. Why? Because this motion, look at this motion. So there's no fixed point no here. This is like a rotation. This is not a oscillatory motion, right? Okay, so this is different. Okay, right. So you should know that periodic motion, the motion, it should be happen again and again and again between a small certain time period, given time period. Okay, right. What about the oscillator motion? It should have some points. Okay, fixed point. Between the fixed point, it's moving around, right? That is the second one. Let's move to the third one. That is our topic, simple harmonic motion. Simple harmonic motion. Look at the page number 3 and the page, the second page. Simple harmonic motion. So they gave some different definition for the simple harmonic motion. But here, what I'm doing here is I'm going to give you a small different definition for this one. I will come back to this definition later. Okay, I'll come back to the definition later because we need to study some equation before understanding this one. So that's why I'm going to give you another definition for the simple harmonic motion here. Okay, right. Can you, I'll tell you. Simple harmonic motion is if an oscillatory motion, listen carefully, if an oscillatory motion happens in a straight line, is known as simple harmonic motion. This is my definition. Okay, right. If a what? If an oscillatory motion happens in a straight line, if an oscillatory motion happens in a straight line, is known as simple harmonic motion. So now onwards, this is the definition for the simple harmonic motion right now. After learning all the equation, I'm going to come back to this question. Okay, right, now write down the second box in this box. The second one. So write down like this. Write down like this. Definition number 2. Put like this. Definition number 2. Okay, right. Definition number 2. Write down. If an oscillatory motion, if an oscillatory motion happens in a straight line, if an oscillatory motion happens in a straight line, is known as simple harmonic motion. Is known as simple harmonic motion. Is known as simple harmonic motion. Okay, right. Is known as simple harmonic motion. So for this question, for this one, so like, can you tell me, let's say, right. So I'm going to draw a diagram here. Draw a picture. Right. Look at this one. This is a spring. There's a mass here. I attached a mass here. Okay, right. So we call this one spring mass system. Okay, the system is known as spring mass system. The system is known as spring mass system. Okay, right. So let's say when we are giving a small force here, or like, let's see, like, let's take this mass and we are pulling downwards and we are releasing it. What will happen? The motion is like what? It's like it will moves like up and down, right? Okay, so this will move like this, something like this. This mass will go up and down. So there's a motion is happening here. So can you tell me the path of the motion? The path of the motion is a curved line or a curved one or in a straight line. This is in a straight line. Look at this point. So this is the center of gravity of the mass I'm taking. So it's going up, coming back, going up, coming back. So this is in a straight line here. Okay, right. So tell me, is this system is a simple harmonic motion or not? Yeah, this is a simple harmonic motion. We can call this SHM. Short term for the simple harmonic motion is SHM here. Okay, right. What about this system, guys? What about this system? Let's say this is a frictionless flow. Okay, right. What I'm doing here is I'm going to pull this mass here and releasing. What will happen? How it will move? Like this, left and right. So this kind of motion is also a simple harmonic motion. This is also a different kind of spring mass system. Spring and the mass is here, spring mass system. Okay, right. What about this one? Let's say a simple pendulum. Simple pendulum. You all know that. You all know, no? The simple pendulum, you all know, right? Okay. So okay, look at this one. So what I'm doing here is I'm taking this bob to this point and I'm releasing. What will happen here is this will move like this. This will move like this. Okay. So this kind of motion is guys, what? Simple harmonic motion, right? What I'm telling here is this motion a simple harmonic motion? Yes or no? Simple pendulum motion is a simple harmonic motion. Here, this is not, because look at the path. The path is in a curved line or a straight line. This is a curved line. Yes, this is a curved line. So this is not a simple harmonic motion. But we can make this motion simple harmonic motion. How? Can you give me an idea for this one? How can we make this motion to a simple harmonic motion? How can we make this? Sorry? Resolving? Resolving means resolving vectors. No. What I'm telling here is I should make this curved line into straight line. How? Shorten the line. Yeah, I can agree with you. Shorten the line. So, what do you mean by shorten the line? What will happen? A simple thing here is, what we'll do here is, we can take the oscillation, we can make the oscillation in a small angle. What will happen? Look at this one. This is like a slight straight line, isn't it? Comparing to this line, this is a slight straight line, no? When we are reducing the angle little by little, what will happen? In some point, the motion something looks like this, isn't it? So this is a straight line, right? So we made this. So we made a simple harmonic motion, the curved line into a straight line. So when there is a pendulum, if someone asking like, is simple harmonic, if pendulum makes simple harmonic motion or not? Yes, it will make only in what? Small angles. Okay, only in small angles. So this is how the pendulum is working here. In your practical handbook, they clearly gave you that. They clearly gave you that. When we are doing simple harmonic motion, I will give you later the practical handbook. The practical book I will give you later. In that handbook, they clearly mention that simple pendulum oscillating in a small angle. So that is very important here. The angle, it should be like 0 to 5 degree. It should be 0 to 5 degree. This kind of little angle, right? Okay, so 0 to 5 degree. It can't be more than this angle. Okay, it can't be more than this. Sometimes in some books that is like 0 to 10 degree. This is the maximum. 10 degrees the maximum. We can't go for like 15 or 20 or 30 degree. It's not a simple harmonic motion, right? You should be very clear about these two things. Okay, right? So yeah, so that's the very important point is here. And let's yeah, we'll discuss that part later. I'll give you in the textbook, right? Okay, so okay, so these kind of motions are here. There are three kind of motion. One is periodic motion, second one is oscillatory motion, the third one is simple harmonic motion. So we can sketch all these three motions in a diagram. So I can draw like this. Okay, right. So I can draw like this. So this is the circle for the periodic motion. Periodic motion. Within this circle, the oscillatory motion is here. Oscillatory motion. Okay, oscillatory motion. So can you tell me, is all kind of oscillatory motions are simple harmonic motion? Is all kind of oscillatory motions are simple harmonic motion? No. Is all kind of simple harmonic motions are oscillatory motion? Is all kind of simple harmonic motions are oscillatory motion? Yes. Why? Because simple harmonic motion is like there is a fixed point moving here and there in a straight line. That is the definition we studied. So we can say within the oscillatory motion, this is the simple harmonic motion. This is the simple harmonic motion. So now you can see all three motions together here. So can you tell me, simple harmonic motion is an oscillatory motion and a periodic motion, isn't it? Yeah, correct. So oscillatory motion is a periodic motion. Yeah, oscillatory motion is a periodic motion because it's happening within a time period, right? Period of time. Okay. Oscillatory motion is a simple harmonic motion. No. Is all kind of oscillatory motions a simple harmonic motion? No. What about the spring mass system? Is spring mass system is oscillatory motion? Yes. Oscillatory motion, no, that is it. Yeah, there is a fixed point moving back and forth. So it's an oscillatory motion. Is spring mass system is a simple harmonic motion? Yes, because the motion is in a straight line. So if there is a fixed point and going back and forth, that is an oscillation motion, that's all. Okay, you got it? Yeah, simple harmonic motions mean that oscillation motion should be happens in a straight line. You got it? Yeah, that's all. Can you tell me motion of a simple pendulum, oscillation motion or simple harmonic motion? It's happening in a small angle. Right, now tell me. It's simple harmonic motion and then oscillation motion. Both are correct. What about the simple pendulum? it's like oscillating in a very big angle. Is that a simple harmonic motion? No, that is a oscillatory motion. That's all. So you can draw this diagram in this box, the big one. Okay, right. Okay, right. I give you some examples here. Sorry. Do you need the mic? Hi. So I give you some right. So I gave you some examples for the simple harmonic motion here. Look at this one, the first one, the image. The first one is like there is a simple pendulum oscillating in a very small angle, right? That one. What about the second one? What's the name of that second image? It's a spring mass system. Very good. You can write it down below that one. If you need, you can write it down, spring mass system. The first one is a simple pendulum oscillating in a small angle. Simple pendulum oscillating in a small angle. Simple pendulum oscillating in a small angle. Okay. What about the third one? What's the third one? In your school days, you all did this, right? Right now also, sometimes you will do like if we have a small gap between the chairs or tables, we'll put the roller inside and we'll move like that. No, right? So those kind of motions also, it's like some small blade. Oh, like so you can see, right? So those kind of motions also, simple harmonic motion. Look at this one. Look at this one. There's a saw is we took a saw. The saw is moving like this. Is this a simple harmonic motion? It is, but in a small angle. Got the point? Yeah, that's so you should aware about that small angle. The angle should be less than 10 or 5 degrees. Okay, right. That's all. So we know that. So there are two kind of spring mass system is there. One is like this is vertical, and this is horizontal. So if they mention, if they are mentioning in a question like considering vertical spring mass system means this one. Considering a horizontal spring mass system, that means this one. Okay, you got it. So these kind of motions are like simple harmonic motion. Simply when they are using like when they are giving question like if there is a simple pendulum means that is in a simple harmonic motion, because they will never specifically tell that like in a small angle. Sometimes if we are facing the problems, sometimes they are giving like two answers. One is like simple pendulum oscillating in a big angle and small angles. If we have two choices, we can go for the less the second one. That means the small angle with that one. If there is no choices, that means if they gave like a simple pendulum is moving like this and the period of the simple pendulum is like they are telling a story, so that means that simple pendulum is moving in a simple harmonic motion. Okay, normally simple pendulum is moving with a simple harmonic motion, but we should aware about the angle. So that's why tell you. Okay, right. So that's all. And we can move for the we can move for the physical quantities related to simple harmonic motion. Physical quantity related to simple harmonic motion. So this is a very important chapter here. Okay, right. Okay, so in a simple harmonic motion, that so we know that if there is a simple harmonic motion is happening, simply you can sketch this one, right? Is this correct? Tell me. So the motion in a straight line back and forth in a same in the same time period. Okay, so this is a simple harmonic motion, something like this. You got the point, right? So this is a simple. Is this a simple harmonic motion? It is a simple harmonic motion, but the fixed point is somewhere here. Okay, so you should know, right? Okay, so that's all. So this is a simple harmonic motion. Simply we can draw like this, right? Okay, let's read the first one. The displacement of an object engaging in simple harmonic motion we are taking as x, right? In simple harmonic motion, the notation x represent the displacement. Okay, represent the displacement here, the notation x. This is very important here. Okay, right, let's read. The distance an object is away from its equilibrium position at any given time is called to distance. So sorry, change that into displacement. Not distance, is displacement. Don't cut down that distance. Above the distance, you can write down displacement. Sometimes they will say distance, or sometimes they will use displacement. So that's why you can write down the displacement above the distance. You got it? Right. Okay. So let's say this is very important, right? This is very important. Look at this one. So can you tell me why I am using the word displacement? What is the difference between the distance and the displacement? Distance is a scalar quantity and the displacement is a vector quantity. Vector quantity means what? It has the direction. It has the direction, magnitude and the direction, right? Normally, from this point, the object is starting, no? From this point, the object or the particle starting its journey. Okay, right. Starting its journey here. Right. It is coming like this, these points, coming back here to the fixed point. Again to this point, coming back to fixed point. Okay, right. Let's say, right. First of all, from this fixed point, if we take like if the right side is positive, the left side is negative. If we take left side is positive, the right side is negative. You got it? Right, okay. So I'm going to tell you, right, the particle is now here. The particle is now here. This is like, students, positive x. This is like positive x. The displacement now here is positive x. Let's say the particle is here. The displacement is negative x. The displacement here is negative x. Okay, right. So likewise, I'm going to sketch the second one. We can say like if this is plus 5 meter, this is also like plus 5 meter. This is in the middle now, the fixed point, right? If the particle is now here, the displacement now here is, students, x is equal to plus 1 meter. For an example, if the particle is now here, I can say now the displacement here is x is equal to minus 4 meter. minus 4 meter. Likewise, it can be varied, right? Okay, so this side is, if we take this side is positive, this side is negative. Okay, right. So this is how the displacement is working here. Okay, right. Yeah, that's all. So what you can do here is, students, you want to sketch these two image in that box. Okay, the given box is something like this. No, please draw both of the drawings like this. Okay, below this one, I'm going to give you some points. So that's why. Please draw these two pictures, images. Normally, waves is a very easy chapter, students. If you study this chapter from the beginning clearly, definitely you can get a good results in final exam, because in waves and vibration, you should do the structure is compulsory. There will be a structure, there will be a full essay. So it's like we can get 12.5 marks there. And for the MCQs, we will get like 7 to 8 questions. More than 20 points we can get from this unit only. It's like 1/5 of the full paper, isn't it? 20 marks, right? It's not joke, right? Yeah. So if you study this part clearly, definitely it's worth for you guys. Okay, right. Finished? Yeah, tell me. Sorry? This is, yeah, correct this one. This is minus 5 meters. This is minus 5, no? This is plus 5 meters. Okay, right. Below that one, write down. If we consider, write down below, between the box, write down below the image. If we consider right side is positive, if we consider the right side is positive from the fixed point, comma, then the left side is negative. Then the next left side is negative. Then the left side is negative. So opposite of this also true. You got it? When you consider the left side is positive, the right side is negative. So opposite of this one of this statement also correct. Okay, so that's all. That's enough for this one. Right. Okay. Look at the second one. The amplitude of an object engaging in a simple harmonic motion. The notation is A. What do you mean by amplitude? Just say, like, what you experienced before about the amplitude. Waves. Yeah. What is amplitude? What is amplitude? Sorry? Right. Amplitude, I'll tell you. Look at the definition. The maximum displacement shown by a particle to a certain direction which participate in simple harmonic motion is called to amplitude. The maximum displacement. So in this simple harmonic motion, can you tell me what is the maximum amplitude? What is the maximum amplitude here? What is the maximum displacement here? What is the maximum displacement traveled by this particle? 5 meters. So the amplitude here is 5 meter. So the maximum displacement is known as what? Amplitude. That's all. So if someone is asking like, so there are two kind of SHM is happening. One is like the amplitude is plus 7 meter, another one is plus 5 meter. Which is which SHM is like the bigger one? The 7 meter is right. Likewise, we can know, we can understand that one, right? That's all. So that's very easy for us. Like you can mark this like this. For this one, for this one, below that, yeah. So within the box, please note this one. Note this one. This is positive A, and this is negative A. Note this one. This is positive amplitude, and this is negative amplitude. Positive amplitude and negative amplitude. This is fixed point. This is fixed point. Okay. This is fixed point. Positive amplitude and negative amplitude. For this one, you can draw some more examples. Like you can draw 2 more examples here. Like A is equal to minus 5 meter. Okay, this is, yeah. Draw these 2 examples as well within the box. There's no statement to write down there, so you can use the box. There's no statement to write down in the box, so you can draw that one. Okay, right. So the maximum displacement traveled by the particle is the amplitude. Is known as amplitude. Okay, so let's go for the third one. So look at the third one. Third one is time period. Time period, or you can say periodic time. Or you can say periodic time. Can you please write this down within the bracket near to the T, capital T in the heading? Simple harmonic motion, capital T, you can write it down within the bracket, periodic time as well. Periodic time. Okay, right. Periodic time. Okay, I'm reading the statement. The time taken by an object in simple harmonic motion to do a complete oscillation is called the time period. So time taken to complete a full oscillation or complete oscillation, right? Okay. So what is the time taken for the full oscillation? That means, like, look at this one. Okay, right. I'm taking like this for an example. The notation of this time period is capital T, guys, capital T. So the object is now here. Okay, the object is now here. So this object is traveling like this, coming, it's going to this point and coming back to the fixed point. Again, it's coming to here and coming back to fixed point. So don't confuse with these arrows. That means the object is in the line, but for the direction, I can't put like in the straight line, no, so that's why I put here. Okay, right. The object is something like moving like this, coming to this point here and here and here. So this is a complete oscillation. This is a complete oscillation here. If we take the time period for a complete oscillation is t, when the object is coming from this point to this point, it will take t by 4, because we divide this into 4 equal parts, no? So one is t by 4. It's like if we say like the time period is 4 seconds, can you tell me what is this one? This is 1 second. The time taken here is 1 second. Again coming back 1 second, 1 second, 1 second. So what's that? Totally 4 seconds. So that is the periodic time or time period. You got it? Yeah. So this is t by 4, t by 4, t by 4 and t by 4. So this is how it's this is how we calculate. So the time period here is capital T going to this point t by 4, coming back t by 4, here t by 4 and coming back to this point t by 4. Okay, this is how it's working. Let's say the particle starting from here. Now tell me how it's going to work now. The particle, there's no rule that the particle should be start from the fixed point. In that line, from anywhere it can start the journey, but it should complete a full oscillation. It should complete a full oscillation. Can you tell me how the motion will be here? Let's say going to the fixed point, coming to here, from this point to this point, and this point to this point. So this is now a complete oscillation. You got it? So the time taken here is t by 4, t by 4. This is t by 4 and t by 4. Okay, right. So I'm going to write down another one. What about this? The particle is starting from this point. Now tell me how it can be. How to complete a full oscillation? First of all, tell me how can we complete a full oscillation here? Right. Going to the fixed point, again to this point, from here to the fixed point here, coming back to which point? This one? No, coming back to this point and again to the initial position. So if you want to complete a full oscillation, it should come back to the origin, right? It should come back to the origin, right? So look at this one. Starting from here, so let's say like this is like the middle of this t by 4. No, this is like we are taking like this is t by 4. So half of the t by 4 is what? T by 8. Yeah. So if this is t by 8, this is t by 4. This is t by 4. This is t by 4. And this is t by 8. So now calculate it. T by 4, t by 4, t by 2. And again, another t by 4 is what? 3 t by 4. Now here t by 8 plus t by 8 what? T by 4. So 4t by 4 is equal to t. So it's a complete oscillation. You can add all the time here and you will get the t. You got it? So this is how it's going to work. Okay, right. So this is a complete oscillation here. I'm going to draw another one also. From somewhere here, we don't know the point here, guys. From somewhere here, it's starting the journey from here. So if it is going like this, can you complete the oscillation? How can we? Tell me. It is coming from this point to this point. How to complete a full oscillation? Tell me. Again to the fixed point. This point to this point. Coming back here. And again, from this point to this point. So this is how it's going to work. So this is also a complete oscillation. So first of all, you should know about the complete oscillation and the time taken to complete a full oscillation is known as the periodic time. So that is capital T. You got it? So that's all, guys. So you can draw these four diagrams in your inside this box. You can divide them into equal 4 parts and you can draw. Yeah. Sorry. Fixed point is the middle one. Yeah. Always fixed point is the middle of the simple harmonic motion. Yeah. Guys, this is for the example only. Yeah? Look at this one, this T by E, T by D is for the example only. It can be vary, like like I took the middle of this T by 4. No? Sometimes it can be here also, here also. It can be vary, right? Okay, yeah. So that's why I didn't put the time period here. Why? I didn't put the time here. Why? I don't know. It can be vary. It can be T by 18, T by 16, or T by 5. We don't know the values, no? So that's why, right? But when you add all the time together, what's the value? T. It's capital T. Draw that 4 diagrams. So there is an equation for the periodic time also. After completing the theory part, that means that after completing the calculations, we'll come back to the equations. Okay, right. Did you all study the circular motion? No, not yet. Okay, I'm going to give you an introduction to circular motion because we need that to prove the equation. Okay, right. It's very easy, so don't worry. So how many biology students are here? No one is biology. All you are like maths. Okay. Well done. Okay, right. So like when you are so sometimes you're already following the mechanics classes, no? You're already following the mechanics, right? So it is not a burden to follow the waves here because it's a very simple subject. Okay, there are lots of theories are there. We should understand the theories well. So that is the only thing. So if you understand the concept 100%, so you can get good results in waves. Okay, right. So the concept, the explanations are very important here in this chapter. So these 4 are examples for the complete oscillation. Complete oscillations. Okay. Okay, done. Yeah. Let's move for the 4th one. The frequency of an object engaging in simple harmonic motion. Right. Can you tell me what is frequency? Did you all study the part, which one? Did you study about the spring mass system? F is equal to KE, mechanics. Don't you study that part? The spring constant, half k square, energy. You didn't go for the 2.5. Where are now, guys? Which part you are in now? Sorry? Projectile motion. Projectile motion. Okay. You came to my class, right? Okay. So who is another one? Where I know? Momentum. 2.3. Okay, right. Okay, fine. So let's see. Okay. So the frequency of an object engaging in a simple harmonic motion. The number of oscillations. Right. Now tell me, what do you mean by oscillation frequency? Frequency is very simple. Number of oscillations in a second. Number of oscillations in a second is what? Frequency. It's very easy, right? Okay. The frequency of an object engaging in a simple harmonic motion. The number of oscillations occur in a second by an object participating in simple harmonic motion is called the frequency. Okay, is called the frequency. Look at this one. Let's say in 1 second, this object is completing 5 oscillations, 5 full oscillations. Okay, in 1 second, this object is completing 5 complete oscillations. Complete oscillation. Okay, 5 complete oscillation. That means the frequency of this object here is 5 second minus 1. 5 per second. Okay, right, 5 per second. So what is the unit for the second? That means per second. What is that? Hertz. For the frequency, what's the unit for the frequency? It's hertz, right? It's hertz. So we can write down like this as well, 5 hertz. Okay, right. I'm giving you another example for this one. Within 2 seconds, a particle is completing like 16 oscillations. In 2 seconds, it's completing like 16 oscillations. 16 oscillations. Now tell me, what is the frequency of this object? 8 hertz. Is it correct? Yeah, 2 seconds, 16, no? So 1 second, how many full oscillation is happening? 8. Yes, so 1 second, it's completing 8. So the frequency here is, we can say F is equal to 8 second minus 1, 8 hertz. 8 hertz. Okay, right. What about this one? In 1/4 second, it's completing like 6 oscillations. So in 0.25 seconds, it's completing like 6 oscillations. Now tell me, what is the frequency here? Always we should consider 1 second. So in 1 second, how many oscillations? 6 into 4, 24 oscillations. Very good. So it's 24 hertz. 24 hertz. So this is how it's working here. Okay, right. So now we are going to derive the equation, the relationship between the frequency and the time period, periodic time. So this is the relationship, guys. F is equal to 1 over T. F is equal to 1 over T. That means frequency is equal to 1 over periodic time. So if you know the periodic time, you can find the frequency. If you know the frequency, you can find the periodic time. You got it? So this is the relationship between the frequency and the time period. Okay, right. So what you can do here is, you can write these down. There are 3 examples are here. This is an SHM. So this is number 1, and this is number 2, and this is number 3. So you should write down this relationship as well inside the box. Okay, write these examples and write down the equation as well.
Recording in progress.
Okay, let's start the lesson. Right, okay. So, so now what we are going to do here is, can you tell me what are the parameters, what are the main quantities in simple harmonic motions? One is displacement, the second one is amplitude, the third one is periodic time, the fourth one is frequency. What is the relationship between the frequency and the periodic time? F is equal to 1 over T. What do you mean by displacement? What do you mean by displacement? The displacement is now where the particle is in the SHM now, right? So that is the displacement. Always we measure the displacement from the fixed point, from the fixed point. What is fixed point? What is fixed point? Fixed point is the point, the middle of the simple harmonic motion. The fixed point is the middle of the simple harmonic motion. Okay, normally it's the fixed, it's the middle of the simple harmonic motion, right? Okay, so that's all. And yeah, So now what we are going to do here is, you didn't study the circular motion, but you know what is velocity, what is displacement, what is distance, you know the equations as well, right? S is equal to ut plus half a t square, the motion equations already you studied, right? Okay. So circular motion is not a very hard subject. It's very easy. So first of all, let's try to understand the concept. Okay, right. So why I'm teaching the circular motion here is, if you all done the circular motion, it's easy to derive the equations here. We need the circular motion part. That's why I'm teaching that part here. Okay, right. So always, it's like, anyway, anyhow it's going to help you. Okay, right. Anyway, you are going to study that part now, circular motion, right? Okay, right. So circular motion, it's not like a motion in a straight line. It's like a movement like this. Okay, right. The circular motion is a particle. It will move in a circular path. Okay, it will move in a circular path, something like this. Okay, right. In this circular motion, guys, the velocity, displacement are little bit different. I'm telling you why. Okay, right. So let's compare the straight linear motion and the circular motion now. A particle is somewhere here, and this is the 0 point. That means here the displacement here is x is equal to naught. So if it is traveling in this side, we can say that plus 5 meter, plus 4 meter, plus 1.3 meter. Likewise, we can say, tell me minus 2.3 meter means which side? This side is moving in a linear motion, But how can we say in a circular motion where the particle is now? How can we say where the particle is now? You can't say, no. Plus 5 meter, plus 4 meter can be put here. Is it possible to do here? No, it's not possible. So what can we do? What can we do here? So what we can do here is, we are using here, students, the angle in radius. Okay, right, radius. So look at this one. I'm considering this is the middle point. This is the middle point. Right, okay. The particle starting its motion from here, and it's moving like this in a clockwise, okay, in clockwise. So let's say now the particle is here. Let's say now the particle is here. What is the, so if you want to notate this particle, how can we say? We can say like, its angular displacement is 30 degree. Its angular displacement is 30 degree. So in a straight line, in a linear motion, we will use what? In a linear motion, we will use displacement. But here, we are using angular displacement. Okay, here we are using angular displacement. Right. So let's say here the angle is theta. If the theta is 30 degree, tell me where the particle is now. It is here. If the theta is 90, here. Like this is what? 180, 270. Now tell me, what about 720 degree, where the particle is now? 720 means what? One full rotation is like 360. Another 360. What is the total? 360 plus 360. 720, right? So here the particle is now. So we can also say 2 complete oscillation it made. 2 complete rotation it made, right? So here the idea you should know here is, in a linear motion, we are using distance, displacement, but in circular motion, we are using angular displacement. We are using angular displacement. Okay, right. So this is like I'm giving you some points like 5 meter. So displacement is now is plus 5 meter. But here we are using angular displacement. Okay, right. So another second point here is velocity. In linear motion, we are using velocity. In linear motion, we are using velocity. The velocity here is like we can say in ms minus 1, the particle is moving with the velocity of, let's say it's like 2 ms minus 1. 2 ms minus 1. So here we are using the velocity. Here we are using the velocity. It's like 2 ms minus 1. But here, this is little bit different. I'm going to explain you why. Okay, right. Let's say right. Okay, I'm going to erase this one. Okay, right. Look at this one. For the angular displacement, right? That's okay, no? Right. So what I'm going to do here is angular velocity. Okay, right. Angular velocity. So the notation for the angular velocity here is, students, omega. Here we are using V. Here we are using omega. This is not a very difficult one, very easy. Look at this one. Can you tell me the relationship between the displacement and the velocity? Can you tell me the relationship between the S and the V? V is equal to S over T. V is equal to S over T. So can you tell me what is this? Velocity is equal to displacement over time. Okay. So now can you convert that to angular velocity? How can we say? Angular velocity is equal to angular displacement over time. That's all. So here their velocity is equal to displacement over time. No, that is really like linear velocity is equal to linear displacement over time, but we are not using that word linear. Okay, Nikang, we are using that what like only the velocity displacement time we are using, but we should mention that one. Okay, but here anyway, anyhow, we want to mention that one here. Can you tell me? So now for the angular displacement, the notation is theta. Angular displacement, the notation is theta. So there V is equal to S over T. Now here tell me. Omega is equal to angular velocity. Omega is equal to, very good, theta over T. You got it? There are displacement over time. Here, angular displacement over time. That's all. Omega is equal to theta over T. So can you tell me what is the unit for the omega? What is the unit for the omega? So we are measuring the angle in radius, normally in radius. Like, let's say it's like, let's say it's like 60 degree. If it is 60 degree, can you convert this into radian? Pi by 3 or pi by 6? Pi by 3, very good. It's pi by 3. It's pi by 3 radian. It's pi by 3 radian. So you can give this angular velocity in 2 units. One unit is degree second minus 1. Normally we are not using here, because if you substitute 60 degree here, it's a degree second minus 1. No, right. Normally we are not using here. The SI unit here is, students, the SI unit here is radian second minus 1. Radian second minus 1. You got this? Right. Again, we are going to move to the angular acceleration. Angular acceleration. For the angular acceleration, we are using the notation alpha. Alpha. Now tell me, what is the equation for the acceleration? Linear acceleration? Tell me. Acceleration is equal to velocity over time. Rate of change of velocity, right? So velocity over time. Velocity over time. What about here? Can you convert that into here? Angular acceleration is equal to angular velocity over time. They are linear velocity over time, no? Here what? Angular acceleration over time. Sorry, angular velocity over time. So what is angular velocity? Omega. Omega over time. That's all. Now, can you tell me what is the unit of this one? What is the unit? The unit here is radian. The unit of the omega, tell me. Radian second minus 1 divided by second, it's what? Radian second minus 2. Isn't it? Yeah, there, what is the unit? Acceleration. ms minus 2, because we are measuring the displacement in meters, but here we are measuring it in radius. Yeah. So here, the unit here is radian second minus 2. Radian second minus 2. Okay, right. So these are the important parameters in circular motion. Okay, right. Like what you want to do here is yeah, first of all, what you can do here is you can draw this image. Okay, draw this image and write down the write down this angular displacement, angular velocity, and angular acceleration. Okay, write this all. This one, this one, this one. This is, you know, you don't need this one, right? Don't write this one. මේක ලියන්න එපා. මේ ටික ලියන්න. Draw this circle and please mention the angular displacement. This is angular velocity, angular acceleration. Do you have any doubts? No. Right. Okay. Finish, right? Okay. So so this is like angular acceleration, right? Okay. So what we are going to do is here is right. Okay, so that's completed now, right? Normally, we are going to we want to know about the angular velocity here. Okay, right? This angular velocity here. Angular velocity is always, so if you want to notate the angular velocity here, it's very simple, right? It's always in the tangent. Okay, so like when we are taking a circular motion here, let's say if the particle is now here, if the particle is now here, guys, the velocity is now, we want to notate the velocity like this, like this. So this is 90 degree. You got it? The tangent, you know that, right? Did you know this one? You already studied now how to draw the tangent for the circle, right? Okay, so this is how it will be looks like. What about this point? If the particle is moving in the clockwise direction, how to draw? Like this. If it is here, like this. This is like 90 degree, okay? This is also 90 degree. So can you draw this one? Uh, please draw this one. So here, write down a note. Write down a note. Write down a note. Velocity is always tangent to the circle. 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 Put the V also here. Look at here. Put the V. Okay, right. In circular motion, guys, this is very important. Huh? Right. In circular motion, please put a small heading, acceleration in a circular motion. Small heading. Huh? Acceleration in a circular motion. 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 Okay, right. Okay. So acceleration in a circular motion. So in a circular motion, the acceleration is little bit different. Okay. The velocity is also different. The acceleration is also different. Now let's say Now if we say like now the object is here, let's consider that the object is here now. If the object is here, the acceleration always towards the center. Okay, acceleration always towards the center. That is the rule. That is the definition. In circular motion, we'll study how it will be and how it came, right? There's a proof for this one, and we'll study that one later. So in circular motion, the acceleration is always towards the center. Look at this one. How we want to notate the acceleration? Like this. This is the acceleration. If the particle is here, this is the acceleration. If the particle is here, this is the acceleration. If the particle is here, this is the acceleration. This is the acceleration. So this is how it's working. This is how it's working. You got it? Right. So please write this. Did you all write the definition? Write down. In a circular motion, the acceleration always in a circular motion, the acceleration always towards the center. In a circular motion, the acceleration always towards the center. The acceleration always towards the center. Towards the center. In a circular motion, the acceleration always towards the center. Right, look at this one. Look at the board, right? Okay. So this is the, can you tell me what is the equation for the, acceleration? A is equal to, tell me. A is equal to omega over t. A is equal to omega over t. If you forget the equation, you can simply remember with the linear motion. Like in the linear motion, we know that A is equal to V over T, So here, alpha is equal to omega over T. This is not A, it's alpha, right? Alpha is equal to omega over T, right? In the circular motion, students, there is a special equation. That is V is equal to R omega. V is equal to R omega. So this is a special equation in the circular motion. Okay, right. V is equal to R omega. This equation gives you the relationship between the omega and V. That is, so this is the equation between the relating the linear velocity and the angular velocity. So tell me, linear velocity is equal to radius into what? Angular velocity. Linear velocity is equal to radius into angular velocity. This is the relationship between the linear motion and the circular motion, angular motion or circular motion. You got it? Right. Okay. In the second note, write down the relationship between linear velocity, the relationship between linear velocity and angular velocity. The relationship between linear velocity and the angular velocity. Linear velocity and the angular velocity is given by, please write this equation, is given by V is equal to R omega. Here, R is radius. Here R is radius. V is equal to R omega. Here R is radius. Radius. Here R is radius. Here R is radius. Okay, right. Right. What I'm going to do here is, if V is equal to R omega, if V is equal to R, look at this one. If V is equal to R omega, what I'm going to do here is I'm going to divide this equation both side by T. I'm going to divide this equation both side by T. So tell me, V divided by T is what? Velocity over time is acceleration. Yes, it's A. A is equal to R into what is omega by T? Angular acceleration. Yeah, omega by T is angular acceleration is alpha. So A is equal to R alpha. So this is also another equation. So write this down. So V over T is equal to R into omega by T. A is equal to R alpha. Write this down. Huh? Right. Another equation is there. Look at this one. Another equation is there, students. Look at this one. Huh? Look at this one. A is equal to V omega. Okay. A is equal to V omega. Write down the another equation. Write down another equation, students. Okay. Right. The relationship between another note. Okay. Right. The relationship between linear acceleration and the angular acceleration is given by, sorry, wait. The relationship between linear acceleration and linear acceleration and linear acceleration and linear velocity and linear velocity and linear velocity is given by linear velocity is given by a is equal to v omega. A is equal to v omega. A is equal to v omega. Okay, right. So A is equal to v omega. Okay, A is equal to v omega. You got it? Right. So tell me, A is equal to V into, students, look at this one now. I'm going to substitute. Okay, right. I'm going to substitute for the omega here. The V is already here. For the omega, what I can substitute? For the omega, what I can substitute? For the omega, what I can substitute? V is equal to R omega. Omega is what? Omega is subject to omega. Omega is equal to V over R, isn't it? Omega is equal to V over R. That's all, very simple. So A is equal to V into, for the omega, we can substitute V over R. So A is equal to V squared over R. This is also another equation. Okay, this is also another equation here. A is equal to V squared over R. A is equal to V squared over R. Now, listen this very carefully. A is equal to V omega, no? Right, look at this one. A is equal to V omega. So, I'm writing this down. A is equal to V omega. What I'm going to do here is A is equal to, for the V, I can substitute, what I can substitute here for the V? For the V, what I can substitute here? R omega. So, I can put R omega into omega. So, A is equal to R omega square. A is equal to R omega square. So, you should write down, so A is equal to V omega. So, you should write down this one and this one. Okay, that's all. These are the equations. And yeah, now we can move for the simple harmonic motion. Write down this one and this one. Okay, right. So, students, these are the short notes for the circular motion. I'm going to repeat you. Just we need only two equations. Okay, in this part, just we need only two equations. Those equations are, one is like A is equal to V squared over R, or A is equal to R omega squared. These two equations, and also we need V is equal to R omega equation, this one. So these three equations are made. So please, can you please highlight this equation? This one, V is equal to R omega. A is equal to R omega square. A is equal to V squared over R. Please highlight those three equations. highlight this one, this one, this one. Sorry, this one, and that one. A is equal to V over R, A is equal to R omega square, V is equal to R omega. Right, that's all. So here I can tell you this equation directly, but what I did here is I explain you a little bit about the circular motion. Without knowing anything, we can't do, right? So that's why I give you an idea. So I'm going to summarize this one. Listen this very carefully. Yeah? Right. Repeat with me. Okay. Right. First of all, there is a linear motion and angular motion, circular motion. In the linear motion, it is linear displacement. In the angular motion, it is angular displacement. The linear motion, so the angular motion, in the linear motion, we will notate the displacement in meters, like plus 7 meter, minus 3 meter, because the displacement is a vector quantity. And also in the angular displacement in a circular motion, we use angular displacement to notate that, to identify where the object is now. We want to identify the position of the object now, so it will help us to know where the object is now, to identify the position. In linear displacement also, to identify the position, right? So it's like if I'm measuring from here, if I am -1, I mean here, this side, +3, that side. I can easily identify. That's the point number one. The second one is in the linear velocity. What is the equation for the linear velocity? V is equal to, so linear velocity is equal to displacement over time. For the angular velocity is angular displacement over what? Time. Angular displacement we will measure in radius, so it's radian second minus 1. For the acceleration, linear acceleration, what is the equation? A is equal to V over T, velocity over time. But in the angular velocity, what we can say? Alpha is equal to, angular acceleration is equal to angular velocity over time. Angular velocity is what? Omega. Time is second. So omega's unit is what? Radian second minus 1 divided by second is radian second minus 2. Acceleration is ms minus 2. Here it's radian second minus 2. You got it? That is the part. And also there are two important factors are there. Angular velocity is always in the tangent of the circle. We want to notate that in the path of the tangent. Okay, tangent of the circle, the velocity is there. Okay, that is the first point. Second point is what? Acceleration always towards the center of the circle. Right. For the acceleration, what is the relationship between the acceleration, velocity, and the radius? Acceleration, velocity, radius. A is equal to V squared over R, or A is equal to R omega squared. What? A is equal to V squared over R. What is the next one? Acceleration in the omega relationship. A is equal to R omega square, or A is equal to V squared over R. That's all. That's all you need. You got it? Right. So now, students, what we are going to do here is we are going to move to the SHM again. So these parts are circular motion. Okay, right. Is the space is enough for you? Yeah, the next side, we are going to move to the next one. Okay, right. You need a break? No, I think, right? Are the teachers providing breaks middle of the sessions? No, right? Okay. So is it boring? Is it boring? No, you can. Okay, right. So let's move to the next one. Okay, right. It's like tired, looks like tired because of the school, right? Always after school classes always looks like this. Okay, so students, we are going to move to the next one. It's like we are going to derive the equation for the simple harmonic motion. Okay, right. Look at this one. It's really hard to get the equation for the simple harmonic motion because the motion is like this. Okay, the motion is something like this. We studied linear motion and we studied the angular motion as well, circular motion. But this is something like middle of these two. So what we are doing here is we are going to consider the projection of a circular motion. Is circular motion is a simple harmonic motion? Think, is circular motion is a simple harmonic motion? No. Because why? It is a periodic motion. Is it an oscillatory motion? No. Why? Because if it is an oscillatory motion, there should be a fixed point. So there is no fixed point. Right. It is a simple harmonic motion? No. Because it is also like if it is a oscillatory motion, there should be a fixed point and back and forth movement. So that this is a circular movement. No, this is not a back and forth movement. But students, projection of a circular motion is simple harmonic motion. What is the projection of a simple circular motion? I'll explain you here. Look at the board. I'm taking a circle. Okay, right. So here I'm taking a circle. A circular motion. A particle is moving in a circular motion, guys. The particle is moving in a circular motion. Right? So let's say there is an object is here. Look at this one. There is an object here, guys. Okay, there is an object here. Okay, right here. So this object is going to move in a circular path like this. It is going to move in a circular path. What I'm going to do here is I'm applying light here. Light. This is light beams. Light beams. Okay, right. So what will happen? So we are applying light in this direction. So there is a ball here and I am placing a screen here. I'm placing a screen here. So you can see the shadow of that particle, isn't it? You can see the shadow. So where's the shadow now? The shadow is here. When the particle is here, where's the shadow now? If the particle is here, guys, where's the shadow now? That is here. The particle is here, where's the shadow? Right. Again, when it's coming back here, so now tell me, when the particle is now here, look at the shadow is here. Here, the shadow is here. When it's here, it's now here. When it's coming back like something, some portion like this, shadow is here, the shadow is here. And when it's coming down, the shadow is here. When it's coming to this point, the shadow is here. So what is this? When the particle is moving in a circular motion, the shadow is moving like this, isn't it? Can you imagine? Look at this one. Look at this one. This is the shadow, the blue color is shadow. Look at this motion. You understood? So is circular motion is a simple harmonic motion? No. The projection of the circular motion is simple harmonic motion. So this shadow is known as projection. Okay. So the projection of the simple harmonic, projection of a circular motion is a simple harmonic motion. So guys, now we know, right? Now we know, like, and also I'm going to tell you another interesting thing here. So if like, can you imagine like this is a graph sheet? Okay, this is a graph like you all maths, right? Okay, then it's easy for me. Right. So this is like y and this is like x-axis. This is like x-axis. Okay, right. This is like x-axis. Okay, right. So can you tell me this is like moving, no? So this particle is now, what is happening? The particle is now moving here, right? Okay. What I'm telling you here is when the particle is moving here, the x-axis and the y-axis also changing here. Let's imagine I'm giving a projection, that means the light beam somewhere here. I am placing the screen here. I am placing the screen now here in this place. I am placing the screen. So now the projection, how it will be, looks like. So the now the light beam is here. Light beam is here now. So the projection now is here. When it's coming here, this point. When it's coming here, this point. Somewhere here, this point. Somewhere here, this point. And when it's coming here, something like this. So here, another simple harmonic motion is happening. So if a circle, in a circle, x and y axis are moving here. If you took the x axis, the motion is like this. If you took the y axis, the motion is like this. There is a chapter in pure maths, like it's circle and straight line. There's a chapter you will study later. In that part, you will study the coordinates and everything here. It's an interesting chapter, and also you can score marks in that chapter also. That's very easy chapter, right? Okay, so this is how it's working. This is how the projection is working. Now tell me, what about the periodic time of this projection and this particle? Same, because it's happening in the same time period now. When it's here, it's here. Again, when it's come to back, come back to the same position, the particle is now here. Right, the same position is here. It's like when it's moving here, it come back to this point, this point, this point, this point. So the both period of time is same. So we can compare these two. So we can get all the equation from the circular motion and we can apply for the simple harmonic motion. So this is the point. You understood? Right, okay. So we are going to we are going for that deriving the equation. We are now going to derive the equation. Listen, guys, I already said you this chapter is very important. The theory, there are lots of theory parts. You can just read it and understand. We can easily understand that one. But this explanation is very important. If anyone missed this important, missed this part, it's really hard to understand what is happening here, right? So, like, okay, so this is the part here. You got it, right? So what we are going to do here is I'm going to explain you how to derive the equation from circular motion to SHM. So the thing here is we are going to find the equation for the SHM, but using circular motion. Okay, right, okay. So the circle is moving like this x-axis, it's moving like this side, and y-axis like this. So this is how the circle made. So let's go for the equations. let's say the particle is here now. Let's say the particle is here now. Okay. First of all, what we are going to do here is we are going to find the equation for the displacement. We are going to find the equation for the displacement using the projection of the circular motion. Using the projection of the circular motion. Okay, right. Right. Listen to this. This is very important. Look at this one. So let's consider this particle rotates angle theta. The particle is now rotate like theta angle, right? This is the angle the particle rotates here. Okay, right, theta. Let's consider this is as theta. So this is the projection, no? This is the projection. In SHM, what is the displacement now? In SHM, what is the displacement of the object? How to find the displacement? Just tell me. How to find the displacement of the object? What we studied from the fixed point, we want to measure. Right. Let's say this is X. Is this correct? Yeah. We are going to find this X now. We are going to find this X now. Okay. Right. Let's take this radius of the circle is R. Radius of the circle is R. This is like I'm making a triangle here. So you all guys now understood what I'm going to do. Can you tell me, using this triangle, what is X? What we can do? We can resolve the vector. R is a displacement. That means this is a vector. So using this vector, I'm going to resolve. How to resolve the, do you know how to resolve the force? Is it possible to resolve the force? Do you know what is resolving the force? I think you forgot. If we consider the force something like this, I'm going to resolve this force into perpendicular position. If this is F cos theta, the perpendicular for this F cos theta is F sin theta. You got this? Do you know? You know? You know, right? Okay. You know, right? Okay. So can you tell me how can we resolve this one into two parts? One is R cos theta. So this is R cos theta, and this one R sin theta. Very good. So X is equal to, we can say X is equal to R sin theta. So we derive the first equation here. X is equal to R sin theta. Okay, right. Again, what I'm going to do here is, I'm going to tell you that the angular velocity of the circular motion is omega. Angular velocity of the circular motion, let's consider the angular velocity of the circular motion is omega. And the time period, so it starts from the journey from here now. Now the object is here now. Let's take this time is t. If this time is t, this time also t. Is it correct? Yeah. Can you tell me what is the relationship between the omega, theta, and t? What is the relationship between the angular velocity, angular displacement, and time? Tell me the relationship. Omega is equal to theta by t. You already studied, no? This omega is equal to theta by t. That means V is equal to S over t. Omega is equal to theta by t. Okay? Omega is equal to theta by t. Can you tell me, if omega is equal to theta by t, how can I rearrange? What I can substitute for this theta? For this theta, what I can substitute? We can subject this theta here, subject the theta. What's the value? Omega into t, no? So theta is equal to what? Omega t. Very good. So I can write like this. R sine omega t. For the theta, instead of theta, I can put omega t. Okay, right, omega t. Right, okay. So if we consider the amplitude of this SHM is capital A. Amplitude of this SHM is capital A. So this is minus A and this is plus A. Let's consider the this is SHM, no, this is simple harmonic motion. This motion is now simple harmonic motion. Can you tell me what is the amplitude of this? Yeah, this is plus A and this is minus A. We know that this is if this is a simple harmonic motion, this is the fixed point. Fixed point. This is the fixed point, and this is the amplitude. Can you tell me what is the relationship between the radius and the amplitude? What is the relationship between the radius and the amplitude? In the SHM, we know that this length is A because the maximum displacement is A. The maximum is here. So this is A. If this is A, can you tell me what is the relationship between the radius and the amplitude? Equal. Can you tell me what is the value here? What is the value here? This is R, no? If this is R, this is A. So both are same. Yeah. R is equal to A. R is equal to A. So I can write the equation, rewrite the equation now. X is equal to A sine omega t. So we derive the first equation successfully. So this is the equation for the displacement. X is equal to, tell me, A sine omega t. If you forget the equation, you should remember what we did now. If you forget the equation, let's say you forget the equation for the displacement. So in your mind, you should do like you want to draw a circle, draw a circle, the radius. So r cos theta, r sin theta. So r sin theta, for the r, we can put A. For the theta, we can substitute omega t. So the equation is x is equal to A sin omega t. Okay. If you are memorizing the equation without knowing what is that is really danger in physics. Not only physics, chemistry, combined, so for the all the subject. Because if we are going to apply an equation, we should aware about the equation where we can substitute this equation gives which values we can get from this equation, what is the relationship of this equation between those physical quantities, what are the physical quantities involving in the equation. So is that vector quantity or scalar? If it is a vector, what is the direction? It is the angular direction or a straight line, or we should know about that one. Okay, these are the things very important. You should remember these things. Okay, right. So what is the equation now? X is equal to A sine omega t. Right. Now we are going to find the velocity. This is also very easy. Can you tell me how to draw the velocity here? How to draw the velocity for the? Can you tell me please for the circular motion? How to draw the velocity here? How can we draw the velocity of this particle in a circular motion? Tangent. Okay, we can draw the tangent, no, the velocity. We studied, no, velocity is in the tangent acceleration towards the center. Okay, this is like this. This is V. Okay, so look at this one, guys. This is very important. Look at this one. I'm going to explain you one important thing. Okay, this is perpendicular, no, this is perpendicular. Okay, right. Can you tell me there are two displacement for this object? Because if we consider in a like graph. If you consider this motion in a graph sheet, like this is now here. Now the particle is here. Let's consider the particle now is here. Can you tell me, is the x coordinate changes? Yes, because it changes, no? It's now the coordinate, x coordinate at the beginning here, now it's here. Is the y coordinate changes? Yes. So at the beginning here, now it's here. So if the x, that means x displacement changes here, coordinates, I'm using the x displacement. So displacement x changes here within the time, that means x changes, displacement change in time, that means that is velocity, no? Velocity. The y displacement change in time, that is also what? Velocity. So there are two velocities involving here. One is x-axis velocity, another one is y-axis velocity. Can you tell me which is related to which one? X-axis velocity is related to this motion. Y-axis velocity is involving in this motion. The vertical motion, y-axis is involving. So for this V, I can resolve this in two directions. What are the direction? One is in x direction, one is in y direction, horizontal and vertical. I am going to resolve this one. Look at this one. I am extending this line. Can anyone tell me what is the angle here? It's very easy. Can anyone tell me the angle here? This is 90, right? What is the angle here? This angle. It's theta. Why? Because this is 90, this is theta, 90. So this is 90 minus theta. This is 90. If it is 90 minus theta, it is 90. This is theta. So the theta plus 90 minus theta is theta plus 90 minus theta is 90, and this 90 total 180. Okay, so this is theta here. Can you tell me what is the x-axis velocity? V cos theta. What is the y-axis velocity? V sin theta. Very good. So I'm going to resolve that one. Look at this. So this is like V cos theta, and this is V sin theta. V sin theta. Okay, right. So now tell me, what is the velocity of this object? What is the velocity of this SHM object? V cos theta O, V sin theta. What is the velocity of this object? V means the velocity of this circular motion object, this object. V cos theta is what? X-axis velocity. V sin theta is y-axis velocity. So this object is moving in x-axis or y-axis? X-axis. So what is the velocity of this object? V cos theta, isn't it? So it's very easy. V cos theta, the velocity, it will looks like this. This is the motion is something like this. So there is two velocities are here. One is V cos theta and V sin theta, right? So one is x-axis and one is y-axis. Can you imagine like this? When the object is somewhere here, when the object is somewhere here, let's say this is V, this is V. Okay, right. So let's consider that this is theta, because when I'm drawing here, this is 90 now. You can draw like this. Okay, right. So I'm just saying, right? If this is theta, let's consider if this is theta, right? So when the object is here now, there are two velocities. One is what? V cos theta. Another one is what? V sin theta. V sin theta is upside, no? So upside means this object is going to move upwards. Okay, this is going to move upwards because look at this one. The position is now here and it's coming back to this side, this one. So this elevation is more than this one, no? So this is the highest point, this is the lowest point. So it want to move in upwards. So that's why that V sin theta helps to go to this position. So now look at this one. This is the position here, x position, and this is it wants to move. It come back to this position. That means this is the this is the displacement between the starting and the ending point. So it should move in this direction. So look at the velocity v cos theta. You got the point. So you should aware about how this movement is working. So students, in this case, so the particle's velocity is v cos theta. You understand? Clear? Is it clear? Is it clear? Yeah. Okay. So we can go for the velocity now. Can write down the velocity. Look at this one. V is equal to, tell me, in the SHM, V is equal to what we can say? V is equal to, this is like V cos theta. V is equal to V cos theta. Okay. For this case, what I'm going to do here is I'm going to mark this V in a different way, like this, because we want to different that one. Let's say it's like simple V. You know the V, right? Like this. It's a Greek letter. V something like this. Okay, right, like this. A simple V. Okay, right. So V is equal to V sin theta. Sorry, is that V cos theta, right? Yeah, V cos theta. V cos theta. Now tell me, guys. Now tell me. V is equal to, capital V is equal to V for the cos theta. For the theta, what I can substitute? For the theta, what I can substitute? Omega t. Very good. It's omega t. For the theta, I can substitute omega t. So now V is equal to V cos omega t. Okay, right. Now tell me, what is V? What is V? We already studied V is equal to R omega in the circular motion equation. We studied an equation V is equal to R omega, no? Right. Look at this one. V is equal to R omega. V is equal to R omega. So here, what is R equal to? What is R equal to? So here, what is R equal to, students? What is R equal to? A, right? Yes, A omega. V is equal to A omega. So we can substitute here for the V, we can substitute A omega. For the V, we can substitute A omega cos omega t. So this is the equation for the velocity in a simple harmonic motion. You understood? Right. Okay. So these are the two important things. One is bending now. Okay. That is acceleration. Okay. That is acceleration. Right. What I'm going to do here is I'm going to explain you that part also. This is also very simple. Look at the board. Okay. Right. The same image I'm going to draw. Let's draw the acceleration now. Look at the board. Look at the board, guys. Okay. Right. Let's draw the acceleration now. Acceleration always towards the center. Very good. This is acceleration. So, can you tell me, we can resolve this acceleration. How can we resolve this acceleration? How can we resolve this acceleration? A, this is 90 minus theta. So this is one is, if this is 90 minus theta, this one is. This is perpendicular, no? If this is 90 minus theta, what about this one? Theta. Yes. So this is theta. So how can you resolve? You can resolve this kind also, this side also. A cos 90 minus theta, A sin 90 minus theta. A cos 90 minus theta, what's the value? A cos 90 minus theta, what's the value? A cos 90 minus theta means A sin theta. Yes, A sin theta. A sin 90 minus theta is A cos theta, isn't it? Yeah. So A cos 90 minus theta, A sin theta. So I'm going to draw here, I'm going to put the acceleration here, guys. A sin theta. So this is A cos theta. I didn't draw that one. Can you tell me, there are two acceleration here, guys. One is A sin theta, one is A cos theta. A sin theta, A cos theta. So which is related to this x-axis simple harmonic motion? A sin theta or A cos theta? A sin theta, because it's happening in x-axis. So the x-axis motion, the acceleration is A sin theta. Okay, right. So I'm writing like this now. Look at this one now. Right. For the acceleration, right. Right. Okay. So I'm going to make a different in this A. Let's take A dash. A dash. Okay. I'm taking this acceleration as A dash because I need to write down the acceleration there. So that's why I'm marking this A dash. That's all. Okay. Right. Look at this one. Okay. Let's do. Look at this one, guys. Now I can say A's acceleration is equal to A dash sine theta. A dash sine theta. Okay. Right. So now the acceleration of if the acceleration of this particle is A, the acceleration is A dash sine theta. Is it correct? Yeah. The V, if the SHM particle's velocity is V, if we consider the velocity is V, so the V is equal to V cos theta, V dash cos theta. That means let's take this is as V dash or small v. Let's take V dash because I'm using the A dash now. So that's why I'm going to use the same V dash. It's easy. Okay, right. So I'm using V dash. Look at this one. Let's say this is V dash, not V, simple V dash. This is V dash. Okay. This is V dash. V dash. V dash. Okay. Yeah. Everything is okay. Right. Now, students, this is the one of the important thing I will give you in the short note as well. Look at this one. We are measuring the displacement from which point? From fixed point. In the right side is positive. Right side is positive. Left side is negative. Now tell me, displacement is positive or negative? This displacement positive. This velocity is negative or positive? Positive. If the displacement is positive, the velocity also positive, because the velocity direction and the displacement direction both are same. Now tell me, what is the direction displacement direction? Right side. But what about the acceleration direction? It is towards the toward this side, towards the right side, towards the fixed point. Now this velocity direction is away from the fixed point. This acceleration is towards the fixed point, but we are measuring the x from the fixed point this side. So in maths also, you should remember that if the displacement is positive, velocity acceleration also positive in that direction. If the displacement is positive in a direction, let's say in this direction, if displacement is positive, in that direction, velocity and the accelerations are positive. So in this direction, if this is minus x, the acceleration, the velocity also minus. So now look at this one. This acceleration is in this direction, so displacement is positive. Sorry, displacement is in this direction, so displacement is positive. Velocity also in this direction, velocity is positive. Velocity is also positive. And the acceleration direction is in this side. So acceleration should be negative, right? Acceleration should be negative. So the reason here is we always measure, the reason here is velocity and acceleration always positive in the direction of the displacement. Okay, so that is the point here. You should always remember that one. If the displacement is positive in this direction, velocity and the acceleration should be positive. If not, that is negative. If it is something like this, it's negative. Okay, right. So we are putting the negative here, and also right again. We'll substitute, guys. A is equal to, we already studied A dash is equal to, A dash is equal to what? A dash is equal to V omega. We studied, no? A dash is equal to V omega, guys. Do you remember? I gave you 3 equations. A dash means acceleration. Okay, A is equal to V omega. A is equal to V squared over R. A is equal to R omega squared in the circular motion. The circular motion I teach you, right? Okay, A dash is equal to V omega. V omega. But V is equal to what? V is equal to A omega, R omega. V is equal to R omega. So we can say A dash is equal to, please substitute for this V, R omega square. R omega square is the equation we already know, right? Okay. So we can write like this. A dash is equal to A omega square. A dash is equal to A omega square. For the A dash, I'm going to substitute here. For the A dash, I'm going to substitute here, guys. A dash, I can substitute what? A omega square sine. For the theta, what I can put? For the theta, what I can put? I can put theta here again. So for the theta, what I can substitute? Omega t, right? Yeah. So A is equal to minus A omega square sine omega t. Sine omega t. So this is the equation for the acceleration in simple harmonic motion. So simple harmonic motion, there are 3 quantities. One is, look at this one. One is displacement. Another one is what? Velocity. The third one is acceleration. For the displacement, the equation is x is equal to A sine omega t. For the velocity, equation is what? V is equal to A omega cos omega t. For the acceleration, the equation is A is equal to minus A omega varkam sine omega t. So these are the 3 main equation. If you understood this one, this subject is like this. Okay, you understood clearly. Do you have any doubts? No, right? So now what you can do here is, you can, there's an image, no, at the last page. You can draw this one and please write these 3 things, right? You can draw. You can write it down quickly. That's all. I know that you won't bring the compass, so I know that I put the circle there, so it's easy for you. So it's easy, right? Okay, so this is the equation for the displacement. And this is for the velocity. And this is for the acceleration. So you should write down මේ ටික ඔක්කොම draw කරන්න. ඊට පස්සේ මේක ලියන්න මේ part එක. ඊට පස්සේ මේ ටික. එච්චරයි. So if you have any doubts, you can ask me. Okay. One, huh? Only draw this one. You don't need this one. Only draw this one. For this particle only, yeah. Which one? Yeah. For the acceleration, this is like a cos theta. If it is a cos theta, this is a sin theta, no? Yeah. You finished? Got it? Okay. So, okay, so today's lesson is successfully finished. We did the equation part. So this is the important part here, students. Okay, this equation part is the important part, and this is our plan. So, like each and every Monday, is it possible to continue on Mondays? Are you all free? It's normally, I think, I will conduct the classes on Monday, theory classes, and also Thursday. Do you have time? Thursday evening. Is it possible? You have classes? No, not the theory. It's like the review. That is revision. Time, evening time. Sorry? Practices. Chess. Okay, right. At what time it's ending? Okay, right. Like what we can do here is we'll start the lesson around 3:30. So you can, I think, after finishing, where are you from? School? Mahamaya. So it's easy, right? Okay. So what I'm going to do here is I'm going to conduct the classes, another revision class. I will start another revision classes. It's like upcoming Thursdays, right? Thursdays revision and Monday theory. Likewise, we can go. And also I will cover up the unit 1 and unit 2 from the beginning. I will do the unit 1 and unit 2 again for the students, those who are following from here. Like if you didn't study the first unit or second unit, or if you have any doubts in those units, you can join that one. That is not like a deep theory, that's like a revision. You already know that. No? Sorry? No. It's like, yeah, the revision class. The unit 1 and unit 2 is a revision class. Most probably Thursdays I will conduct that one. Okay, so we can do the revision class like 2 hours, 2.5 hours. It's enough for us, right? For the theory part, we need some more time. Like today we did like 3 hours. 3 to 6 is 3 hours. Is it possible to end up the class around 6:30? Is it okay? It's fine. So it's fine. Yeah, the maximum I will take like at like 3 to 6:30 maximum, not like 7 or 8, and then I will not conduct the classes. So we'll do like that. Okay, right. So today I'm going to give you a overall view, overall summary note for this chapter. We started the chapter unit 3. In that unit, we started the oscillations. In the oscillations, there are 3 types of motions are there. What are the motions? Tell me the motions. Periodic motions mean the motion, it will happens again and again in a certain time period. That is periodic motion. The second one is oscillatory motion. Oscillatory motion is there is a fixed point. So in that from that fixed point, the particle or the object should move back and forth. Okay, back and forth, not in a straight line, in a back and forth movement. So that is a oscillatory motion. So there should be a fixed point, and it want to move from that fixed point back and forth. That is oscillatory motion. The third one is simple harmonic motion. Tell me, if the oscillatory motion happens in a straight line, that is simple harmonic motion. Okay, so we can give a very good example. So if an SHM, if a simple pendulum oscillating in a big angle, that is a oscillatory motion. In a small angle, that is a simple harmonic motion. This is the difference between that oscillatory and the simple harmonic motions. And also normally that spring mass system, they can horizontal and the vertical spring mass system always moves in a simple harmonic motion. And also what about the oscillating ball in a water pond? That is what? Simple harmonic motion, that is moving like this, no? Straight, like vertical oscillatory motion. So that is something like this. So those motions we studied. After that, we'll move to the simple harmonic motion. Okay, right. After that, after complete that one, we'll move to the simple harmonic motion. In that simple harmonic motion, there are 4 quantities. What are the quantities? What are the quantities? Displacement. If we took displacement, always measure from the fixed point. if in one direction, if that is positive, another direction opposite is negative. And the second one is amplitude. Amplitude is the maximum displacement traveled by the particle is amplitude. The third one is what? Periodic time. Periodic time is the time taken to complete a one full oscillation is what? Periodic time or time period, capital T. Okay. The fourth one is frequency. Frequency is number of oscillation per second. So that is like frequency. What is the relationship between the periodic time and the frequency? If it's equal to 1 over T. So that is the equation there. And another one. So we came for the circular motion basics. In the circular motion basics, we studied the displacement and the angular displacement. So the angular displacement always in radius, the unit is radius. The angular velocity is equal to angular displacement over time, radian second minus 1. The velocity always in the direction of the tangent of the circle. That is the another point, right? So tangent of the circle, the velocity is always in the tangent of the circle. And the acceleration is equal to angular velocity divided by time. The acceleration always towards the center of the circular motion. We studied two main equations. P is equal to r omega, A is equal to r alpha. Okay. Another one is A is equal to V omega, A is equal to r omega square. This is the relation between the A r omega, A r V, A is equal to V squared over R, another equation. Okay. Right. These are the equations we studied. And then we move to the we move to the projection of the circular motion. Projection of the circular motion is always what? Is a simple harmonic motion. Okay, right. So we derive the equation using the circular motion. So and we got the equation for the x is equal to what? A sine theta. Sorry, yes, A cos theta, A sine theta. X is equal to A sine theta. For the theta, we can apply omega t. So x is equal to A sine omega t. For the velocity, it's V cos theta. So V is equal to V cos theta. For the V, we know that V is equal to R omega. So V is equal to A omega cos theta. For the theta, we can apply omega t. So V is equal to A omega cos omega t. For the acceleration is equal to minus A sine theta. Why we put minus here? Because the acceleration is towards the fixed point. Okay, that is opposite to the direction of the displacement. That is opposite to the direction of the displacement. So that is toward the center fixed point. So that is A is equal to minus A omega square sine theta, because A is equal to, we know that A is equal to V omega, V is equal to R omega. For this, A is equal to R omega square. So A is equal to, for the R, we can substitute A omega square. So A is equal to minus A omega cos, sine omega t. A is equal to minus A omega square sine omega t. Only the displacement and the acceleration involved in sine, only the velocity in cos. For the velocity only, there is a cos. Acceleration and the displacement is in sine. Another one is, for the acceleration only, we have the notation minus. Why is the minus is there? The acceleration is opposite to the direction, displacement. So that's the reason. And also we can say like, because acceleration is always toward the fixed point. So that's why A is in minus. Okay. So that's all. You all understood today's lesson. Is it clear? Right. So this is how we will conduct the classes. And yeah, we'll move on. So we will conduct the classes continuously. If you need any extra sessions, I will put that in online as well. So if it is possible to, in some days I will come here and I will do the online session as well. If we need to do more questions in that, there are two tutes given. Please take out the tutes. Please take out the tutes. One is like homework sheet. So homework sheet, there are some questions are there. In the MCQ sheet also there are some questions are there, but it's not enough to, it's really today, after finishing today's session, there's no question to do, because this is very basic. For the next class, we can do 25% of the questions. Okay, we can do after completing the third or fourth class. Definitely we can cover up all the lessons. It's very easy, right? Okay, that's all, students. Let's wind up the session. We'll meet in our next class. So I will let you know about the Thursday's session. The next theory class is on Monday. I will update you about this week Thursday session as well. Okay, right. Okay, thank you so much. Bye. Yeah. Which one? This class did. What about the Tuesday? Do you have class? Tuesday evening. I need to check out with the availability of this classroom. So I'll check it and let you know. Okay. Most probably it's Monday. It's fine. I think it's fine, right? So I'll try to keep the classes. Is it okay? Tuesday is fine for you. What about Tuesday for you? For you, okay? Tuesday is okay. Yeah. Monday, Tuesday, Thursday, all 3 days is okay for you? Huh? Sorry? Wednesday, you can't. What about Thursday? Thursday is fine, right? So what about, shall we keep the classes on Thursday, Tuesdays? Tuesdays, theory classes on Tuesdays. Yes, 3 to 6, same time, like this. Okay, I will confirm the date. So please, if it is possible, you can contact, you can send me a message so I can arrange the time. Okay, you can take my number, note 777. You can WhatsApp me. Yeah? You should mention that from number 0, your name, and you can text me. Okay, so my number is like note 777 425. Note 777 425 707 707. So try to attend the physical classes. So another important thing here is I will definitely complete the theory within the time period. And I will do the revision in first unit and the second unit definitely. So you don't need the theory part for that one. Like I will do the revision, like I will give you a short theory, and Tagala we can do all the questions. That class is based on the question class, model paper class likewise. Okay, that revision class is fully question, right? I will teach you only the 20% or the 10% is the theory, right? All others are questions. So I will explain you the key points and the important points, and I will definitely explain you everything. Okay, right? That's our plan. So we'll meet in our next class. Thank you so much. Okay.